Let's examine the types of metals. Metals used for engineering purposes are classified as ferrous metals, with iron as the main constituent, and others like aluminum, copper, zinc, lead, bronze, chrome, and titanium as non-ferrous metals. Iron, which is by mass the most common element on Earth, is by far the most important of the metals used in construction. It's available in abundance but does not occur freely in nature. Metallic or native iron is rarely found on the surface of Earth because it tends to oxidize. Most of the iron in the crust is found combined with oxygen as iron oxide minerals such as magnetite, hematite, limonite, iron pyrite, siderite. The fundamental chemical principles in extraction of iron from the ores is very simple. Heating the ores in the presence of a reducing agent will result in the formation of carbon monoxide or carbon dioxide liberated as a gas with and metallic iron. Industrial iron production starts with iron ores, principally hematite and magnetite. The iron ores is dressed by crushing it about 50 mm cubes. The conversion is typically conducted in a blast furnace. Carbon is provided in the form of coke. The process also contains a flux, such as limestone, which is used to remove silicaceous minerals in the ore. The coke and limestone are fed into the top of the furnace, while a massive blast of heated air is forced into the furnace at the bottom. In the furnace, the coke reacts with oxygen in the air blast to produce carbon monoxide. The carbon monoxide reduces the iron ore hematite to molten iron, becoming carbon dioxide. The flux present to melt impurities in the ore is principally limestone and dolomite. In the heat of furnace, the limestone flux decomposes to quicklime. Then calcium oxide combines with silicon dioxide to form a liquid slag. The slag melts in the heat of furnace. In the bottom of the furnace, the molten slag floats on top of denser molten iron, and apertures in the side of the furnace are opened to run the iron and slag separately. The iron, once cooled, is called pig iron. The traditional shape of the molds used for pig iron ingots was a bracing structure formed in the sand with many individual ingots at right angles to a central channel or runner, resembling a little litter of piglets being suckled by a sow. Pig iron is not pure iron, but has 4 to 5% carbon dissolved in it with small amounts of other impurities. As the carbon is the major impurity, the pig iron becomes brittle. Its compressive strength is high, but it is weak in tension and shear. Pig iron does not rust and cannot be riveted or welded. Pig iron is classified as Bessemer pig, foundry pig, forge pig, and mottled pig. Foundry pig, also known as gray pig, contains sufficient quantity of free carbon and produced when the furnace is provided with sufficient fuel. With gray pig, water pipes, grits, radiators can be molded. Cast iron. Removing other impurities from pig iron results in cast iron. Pig iron is remelted with limestone and coke in cupola furnace. It is then poured into molds of desired size and shape. It contains about 2 to 4% carbon. Methods of casting include sand, hollow, vertical sand, centrifugal, and die casting. Wrought iron is considered to be pure iron, produced by removing the impurities of cast iron. Wrought iron is ductile, malleable, tough, and moderately elastic. It can be forged and welded. It effectively resists corrosion. At about 900 centigrade Celsius, wrought iron becomes so soft that its two pieces can be joined by hammering. Steel is an alloy of iron and other elements, primarily carbon. By suitably controlling the carbon content, alloying elements, and heat treatment, a desired combination of hardness, ductility, and strength can be obtained in steel. On the basis of carbon content, steel may be classified as dead mild steel, medium carbon steel, high carbon steel, or hard steel containing more than 1% carbon. The most prominent present-day steel-making process is the Bessemer process. The pig iron is first melted in cupola furnace and sent to Bessemer converter. Then the molten material is poured into molds to form ingots. Mild steel, also known as low carbon or soft steel. It's ductile, malleable, tougher and more elastic than wrought iron. It rusts quickly. Its ultimate compressive strength is 800 to 1200 Newton millimeter square, and tensile strength is 600 to 800 Newton millimeter square. It is used in the form of reinforcing bars, roof coverings, and sheet piles. High carbon steel. It's also known as hard steel. It is tougher and more elastic than mild steel. It can be forged and welded with difficulty. Its ultimate compressive strength is 1,350 Newton square meter, and tensile strength is 1,400 to 2,000 Newton square meter. High carbon steel is used for reinforcing concrete and pre-stressed concrete. It can take shocks and vibrations. Heat treatment. The object of heat treatment is to develop desired properties in steel. A steel of given composition may be made soft, ductile, and tough by one heat treatment, and the same steel may be made relatively hard and strong by another. The most common are annealing, quenching, and tempering. Annealing is the process of heating the steel to a sufficiently high temperature to relieve local internal stress. It does not create a general softening of the product, but only locally relieves strain and stresses locked up within the material. Quenching involves heating the steel to create the austenite phase, then quenching it with water or oil. This rapid cooling results in a hard but brittle structure. The steel is then tempered, which is just a specialized type of annealing to reduce brittleness. The result is a more ductile and fracture-resistant steel.